Okay, here's a What the Physics video. This one is about rotational stuff, and all I'm doing is just trying to introduce you to the concepts. So we've actually already been introduced to some of the concepts when we were dealing with uniform circular motion. So reviewing back to that unit might be a wonderful idea. We had translational motion. That's when an object was moving from point A to point B. We had rotational motion when that is the object spinning in place. So it's spinning round and round and round, but the object isn't really going anywhere, as in no motion from A to B. And then we can combine them together, translational and rotational, okay? And we have examples for each one. So the translational one, like a car, the car body itself moving down the street, or you walking down the hallway on your way to physics. Yes, awesome, that's what I did today. Rotational example, like the wheels of a car spinning on ice, or maybe you've got a basketball and you've got mad skills and you can twirl it on your finger. I can't do that. Oh wait, I'll try it right now. Hey, I'm doing it! Oh, look at that! That's awesome! Wow!
Wow.
Yeah, there's no basketball right now. Okay. And then finally, if I were more likely to actually just drop the alleged basketball and it kind of rolls away, that'd be an example of translational and rotational. Okay? Okay. No one would have ever known, by the way. We could have gone along with it. And, yeah, no. Okay. Moving on. Angular motion. It's all Greek to me. It's because it's Greek letters. Okay. So anytime we're going to be dealing with angular motion, we're going to deal with Greek letters. And some of these, of course, we are already familiar with, such as theta. Okay, that's referring to the angle. Now, in this case, we're going to be talking in terms of radians. So yes, we are once again dealing with that evil concept of radians instead of degrees, but that's the deal. So if we're given something in degrees or revolutions or rotations, we do have to convert into radians to make it official. And then we can see this rounded off W looking thing that's called omega, and that's the angular velocity, which is in radians per second. And then the little fishy looking guy, that's the alpha. That's the angular acceleration in radians per second squared. Okay, in case, even though you're in trig right now or beyond that, you just had trig last year, or for some of you geniuses, you had it like back when you were in 4th grade or something, maybe not quite that long ago. Anyhow, to convert radians and degrees, you just use that, right? 2 pi radians is 360 degrees. Okay, so even though this is a very different way of thinking of things, we've never had to think about things rotating before, I mean, other than basic circular motion, but never really beyond that. The nice thing about this is it's so similar to everything we already know. It's going to make the transition pretty easy, I'm hoping. So most everything that we're talking about rotation-wise can fit in with some type of linear version. So omega, which was the angular speed, is just, instead of saying distance divided by time, we say the change in angle divided by time. Okay? Alpha, which is the acceleration, is change in omega divided by delta t. Delta t doesn't get to change into a Greek letter. So, okay, so position is x. In linear, in circular, we have theta. Yeah, just going back and forth. And in fact, we can use these on all the big 5 equations. Anytime there's a delta x, we just take that out and put in a delta theta. Anytime there's a v initial, we take that out and put in the omega initial. There's an acceleration, we put in alpha. There's a omega final, we put in, I'm sorry, if there's a v final, we take that out and put in the omega final. So that makes it really simple. Good. So if we take a moment to think about a ceiling fan, you said, oh yes, I often take moments to think about ceiling fans. A ceiling fan just turned on can spin up to 210 RPMs, rotations per minute, which we already said we're not going to use RPMs, we've got to convert, yeah? In 45 seconds. RPMs would be what in terms of physics concept? Is that a time? Is that a what? It's a frequency, which we recall can convert into angular speed with relative ease. Okay, we got to get it into seconds, and then we got to turn it into radians per second. Yes? Okay. What is the ceiling fan's angular acceleration? Notice this is not centripetal acceleration, the angular acceleration. And then how many revolutions have occurred after 45 seconds? And don't forget to use the radians. Okay, take a moment. Okay, so hopefully you paused the video as well, and you were working on this yourself. You say, Fair, what am I supposed to do? How am I supposed to get this? Well, drawing out a nice sketch of what's going on, listing out the variables, and so on. We already mentioned the 210 RPM is a frequency. We can easily convert that into the angular speed or rotational speed. I use those terms interchangeably. I don't know if they're pretty much the same thing as far as I know. Anywho, we can do that by first converting into rotations per second. So the units would be hertz, yeah? And then we say, oh, well, the frequency is related to the omega by just taking the frequency and multiplying it by 2 pi, right? Right. Because then it would be radians per second, yes? Okay. Anywho, so we have the initial omega is going to be 0. The final omega is, what did we get in terms of radians per second? People do the calculation. Okay, well, 3.5 was for revolutions per second. Okay, so that's just converting from RPMs into RPS. Okay, so that's a good first start, but then what?
Then you multiply it 2 pi to get 22 radians per second.
Great, okay, so that's what I was trying to remind you of there, folks. It's an easy thing to forget, and unfortunately, if you mess up there, it kind of screws up everything else, yes? Okay, so you got to make it in radians per second, not revolutions per second. You say, oh, but Fair, it asks about it in terms of revolutions. Right, I know, but in order to use some of these equations, we got to make sure we're using the right units. Okay, so anywho, we have the time is 45 seconds. So I've got my initial, my final, and my time. And we're looking for the angular acceleration. That's going to be the alpha. Okay? So just like with linear, acceleration is delta v over delta t. All I have to do is say delta omega divided by delta t. Yes? Okay? So the 22 radians per second minus 0 because final minus initial, right? Okay, and dividing by the time, which was 45 seconds, that gives me approximately half a meter per second squared. Oh, I shouldn't have said meters per second squared. Let me pop over to my version here. Okay, I will need to fix that. That should be 0.49, except not meters per second squared. Shame on you, Fair. Okay, the angular, it's going to be radians per second. So please fix that on your papers. Okay, is that what other people got, by the way? Okay, yes? Yeah, sure, fair, I guess so. You don't make mistakes after all. Oh, wait a minute. Okay, so that's the angular acceleration, which is different from centripetals, and we'll discuss this in a moment. But centripetal acceleration, remember, is inwards. Angular acceleration is going to be tangential. How many revolutions have occurred? Okay, well, we're able to convert into total, into angle, and we convert that into revolutions, and we get that. And it's delicious. I do want to emphasize it is a really big deal if we are in radians or not. Pretty much if you see a Greek letter, you should be in radians. Moving on, connecting linear with angular. This is just, well, it's supposed to be a visual of kind of the stuff that we already know. So in terms of S being the arc length and R is the radius, if this was something that you learned back in geometry, okay, and then this is something we had actually talked about earlier this year. If we were talking about the tangential speed or velocity, that's the speed, say like right here or here or here, some point at some distance from the center. It's going around here. This one has a larger tangential velocity than the previous one, and this one has the largest, and that's all because of the radius. Now, if it's also because of the omega here, as we can see, they're proportional. The product is proportional to the tangential velocity. So if you increase one, you're going to increase the left side. Centripetal acceleration, we recall from uniform circular motion. Well, we can express that in terms of omega. And once again, we've got to have the R in there, or else it doesn't tell us about a specific spot. It would just be telling us about the angle. And then the tangential acceleration. So this is the first time we're really getting into an object speeding up. So it's not simply going around in uniform circular motion. It's going around faster and faster and faster, as we were trying to get across the point in terms of a ceiling fan. The takeaway from this is, in order to go from the Greek letter to the Roman letter, in other words, the rotational to the linear concept, you've got to multiply by an R. I mean, there's maybe a little more to it than that, but that's the easy conversion. Okay, so you might be saying, okay, I understand centripetal acceleration, and that was from what we learned earlier in the year. And of course, there's linear acceleration. In terms of the Greek counterpart, what do we mean? So it is very important that you are careful seeing what type of acceleration you're dealing with. Centripetal, that just means you're accelerating toward the center. That just means you're going around in some type of circular path. If we're talking about alpha and or tangential acceleration, that means the object is going faster and faster in that, or slower and slower in that circular path. Okay. And of course, the difference between the alpha and the tangential acceleration. The tangential acceleration is, we're talking about a specific point along the radius. We'd say, oh, this point right here is one value, some point farther out is going to be a different value. For alpha, it's going to be the same throughout the whole radius, because we don't really care about radius, it's only angular stuff. But there are the three accelerations, so make sure you understand the difference among them all. Okay, so speaking of things rotating or spinning, why would they spin in the first place? So you've probably pushed on an object before. Your textbook talks about you push on a textbook. You can push on it in one spot, and it'll move, but it'll also start to rotate this way. You push on another spot, it'll move and start to rotate another way. If you push at what's called the center of mass, and you get the net force going on right there, It's not supposed to be spinning. I say not supposed to be, just to clarify, if all the net force is kind of centered around there. And we'll discuss that when we incorporate torque a little better. Okay, so pushing on this bar right here, if I were to just push on it right here, if it were sitting on the desk, it would kind of rotate around this way. If I push on it here, it would rotate around this way. If I pushed on it right on the center, it would just move forward in whatever direction I pushed it. In this case, this is, of course, a bar that's kind of hanging in the air, and pushing up on it here and here. Notice these forces are different sizes. Once again, when we get to the torque stuff a little better, we'll talk about that. Okay, now I did use the word center of mass, and just to give a quick explanation of that, it's if we were to simplify the object down to a point mass, then that's where the center of mass would be. And sometimes we alternate center of mass and center of gravity. As far as I'm concerned here, they're the same thing. Technically, for it to have a center of gravity, there needs to be a gravitational field, but we're not going to be picky in terms of, hey, there's no gravitational field here. Anywho, if we were to look at these, this image right here, it's going to balance the ruler on our fingertip. That's because that's where the center of mass is. If we were to look at the forces, just like here, the gravity is right down here, because if we were to concentrate all the mass there, once again, center of mass. So if I'm pushing up right at that same point, there's not going to be any angular motion. You look at these folks here, we have the people's center of mass marked out here, and you can see that they have supports on either side or right below where their center of mass, center of gravity is. If her center of mass were over here, I'm not quite sure how that would have worked out, but the point is she would be very likely to tip over. Okay, this guy standing here, if he were to lift up this leg here, he would fall over to his right, and so on. If this person with the kid leans forward too much, they would fall forward. If they lean backward too much, of course, they would lean backwards. Okay? I mentioned the term torque. Torque is going to incorporate force, but not just any random force in any particular direction. We got to pay attention to direction, as well as the distance from the potential axis of rotation. So we're talking about how big the force is, and how big the distance is, and the angle at which it's being exerted. So I'm going to assume that people have used some type of device before, some type of tool, like a wrench, for example. Okay, let's imagine you're using the wrench here and you're turning it. You've probably noticed that if you were to pull from, say, right here, that's going to be pretty challenging to get the thing to move. If you pull from farther out, it's going to be a lot easier. As shown right here, a larger force would be needed for a small radius. A bigger radius is going to mean a smaller force. The other thing they incorporate here is this angle business. Usually we would just be pulling perpendicular to the tool. In this case, they're not doing that to demonstrate, hey, it does matter what the angle is. If we put all these things together, we get torque. The symbol for that is the Greek letter for T, that's a tau, and that's R times F perpendicular, or R times F times sine, then this is phi, where phi is the angle between the force and the radial arm. You can use whatever angle you want, but oftentimes they'll just use this. It's nice and easy if they are perpendicular to each other, then that means we're going to have our maximum torque value. If they're not perpendicular to each other, oh well. You imagine pushing open a door. If you were to push open a door from just pushing on where the door handle is, first of all, that's going to have a very large radius. You wouldn't need much force in terms of pushing it open or pushing it closed. If you've ever read The Hobbit or Lord of the Rings or anything, I always thought it was kind of weird that Hobbits' doors have their door handle right in the center. And as I was reading through that book recently, thought, well, to get the proper amount of torque, that just means if you got to pull with a larger force, and isn't that silly? I don't know if Tolkien was thinking that too, but anyhow, I'm sure plenty of other folks have thought the same thing, right? Because everyone thinks about physics. Sure. Let's do an example problem. How big is Kitty? So we have kitty cat on one end of a seesaw, and we put your little brother on the other end. Your brother's mass is 18 kilograms, and he is 1 meter away from the seesaw pivot point. Kitty is 2.9 meters away from the pivot point of the seesaw. Of course, that's really, really big. That's a very large distance, but we're pretending it's a really big seesaw. What is Kitty's mass? If we're balancing like this, then that means the torques are going to balance. So we saw from the previous slides back here, remember when we said the closer we are, the larger the force is going to be needed to balance out. Farther out, a smaller force. So hopefully that helps you realize, first of all, that Kitty is going to be a smaller mass than your little brother. If Kitty were a bigger mass than your little brother, you've got all sorts of other problems. But take a moment and work through here. Okay, so in order to get this balanced out, we said we got to balance out the torques. Luckily, we don't really have to focus on the angle too much because gravitational is the force for each of these, and that's going to be downwards, and the seesaw is going on the x-axis, so they're automatically going to be perpendicular to each other. So all we have to do is figure out the r and multiply by the f. So we said for your little brother, it's 1 meter and then times his force, which is 18 kilograms, that's the mass, and then times little g. And then for kitty cat, we've got 2.9 meters times some unknown mass, and then times little g. Now, we said in order for this to balance out, the torques will have to balance out. So the force trying to get it to move this way, which we would consider to be in a negative direction, it's got to be the same size as the torque pulling it in this direction. That's going to be considered the positive direction. So in other words, they're going to be the same size. Okay. However, to make sure we truly understand that, let's do a sum of the torques equation. There's no rotation, so the sum of the torques, we're doing it just like some of the forces, is torque of Kitty minus torque of your brother. We already mentioned how phi is going to be 0, or I'm sorry, phi is going to be 90, so that's going to be sine of 90 is 1. So these two minus these two will equal 0. Okay, and that means they are equal to each other if we bring one to the other side. And all I have to do is solve for Kitty's gravitational force. Now, technically, because I'm solving for the mass, I can actually cancel out the acceleration due to gravity on each of these. And look at that, 6.2 kilograms, which is, a pretty sizable kitty cat. Okay. So, now that we've talked about rotation, how can we avoid rotation? If we were talking about a net torque being 0, that means we're not speeding up, we're not slowing down. If we think back to when we were doing Newton's first law, objects in motion stay in motion, objects at rest stay at rest, unless there's a net outside force. So the object will have a constant velocity, assuming there's no net force. It doesn't mean the object will move or not move. It'll just keep doing whatever it's been doing. So when we say, how do we avoid rotation? Well, if we're already not rotating, if it's just sitting there, then we just got to make sure that there's not going to be any net torque on it. If we already are rotating, well, that's a whole different issue. We'd have to make it come to a stop. It's like saying, how do we avoid motion? Well, we'd have to, that's different from how do we avoid changing motion. So, anyhow, let's say the object is not rotating. So we've got this person sitting on a desk or a chair or something. Okay, and here's the center of mass. If he were to lean back too far, what would happen? Well, the center of mass is no longer above his support area, so you know he would rotate. You've probably been in this situation before. What are you going to do if you start to tip over? Well, what you could easily do is you'd swing your legs out forward, and that would actually keep your same gravitational force on the legs, but it would pull them out farther. So that would increase the torque pulling you down this way. Let's assume, though, this is a rigid object. You don't move. Okay, you're able to be tipped backwards, but otherwise you're staying completely stiff here. What would we need? We would need someone pushing upwards here, like on his head area or shoulders, or something extra pushing down here. Okay, so like if you had someone pushing down on your feet, okay, that would increase the torque by keeping the object rigid. Physics.